Hey there, class. Mr. Husky here. Hope you're having a good day so far. We're continuing with Chapter 8, which is all about exponents, and today is exponential growth. You may have heard something, so if you hear me say the word something grows exponentially, is that really big or really small, or what is that? Yeah, it's a really big. So basically, an exponential growth function is it increases by the same percentage each time. So basically, it takes the previous number and it multiplies it by an increasing percentage every time. And when you do that, the net sum of doing that every single time is that it gets really big really fast. Okay. So this is going to be what we're talking about today. It's really useful with banking, with interest on accounts and stuff like that, and modeling. For example, there's a we're going to be talking about chipmunk populations here. So modeling populations, modeling just modeling in general, I guess, is a really useful tool, the exponential growth function. Okay, so let's get right into it here. Exponential growth is a quantity that increases by the same percent in each unit of time. All right. So we have this is our growth model right here. Y equals C times 1 plus R all to the t power right here. Y equals C times 1 plus R all to the t power. Let me circle that a little bit more delicately. There we go. Okay, so C in this value, so Y is going to be what we're measuring. C is going to be our initial value, what we start with. So basically, you're going to multiply C by a growth factor every time and take that to the power of a time value, and that will determine at any given point how much the Y value has increased, okay? 1 plus R is called our growth factor. 1 plus R is called our growth factor. And the way you know that it's a growth factor, it's just whatever is in parentheses is going to be our growth factor, okay? Whatever's in parentheses is going to be our growth factor. R is going to be called a percent of increase. Our percent of increase. And you also want to be careful, you want to convert it to a decimal. I want to convert it to a decimal. And R is going to be how far the growth factor is from 1. It's how far the growth factor is from 1. Okay? All right, so let's get right into it now. So we have a problem here, a word problem. It says you invest $1,000 in an account that pays 6% annual interest compounded yearly. What is the account balance after 10 years? Okay, so C is our initial value. What's our starting amount? Can you find the starting amount in this problem? Hopefully you said it's 1,000. 1,000 is what we start with. That's our C. Okay. A growth factor is kind of hard to tell sometimes, but there is a percent of increase here. Do you see the percent of increase? It's increasing by 6% yearly. So we're going to write R equals, we got to be careful here. One of the ways you can mess this up is you just put 6. R does not equal 6. R equals 6% as a decimal. How do we convert 6% to decimal? Well, we move the decimal 2 to the left, right? So 1, 2, so it's actually going to be 0.06. Okay, the R is not 6, it's 0.06. If you put 6, that would be a 600% increase, which is not the same thing, okay? So percents converted to decimals, move the decimal 2 to the left. All right, what else do we know? Well, our time, our T, oh, I forgot to fill that out, right? My bad. So T is time in years, usually. Time in years, usually. Okay, so what's our time for this part down here? Our time is 10, and what is the account balance? That's what we're ending up with. That's going to be our Y. That's the ending result. So we're going to plug into this formula, Y equals C times 1 plus R all to the T. We're literally just going to plug stuff in. So we have Y equals C was 1,000 times 1 plus R is 0.06 times T, which is 10, or to the power of 10, sorry. So y is going to be approximately, when we plugged it into our calculator, make sure you ask me to show you how to do that in class. But basically, you're going to plug it into your calculator exactly like it looks, and you're going to use parentheses and exponents. So you should get approximately $1,790.85. So that is going to be after 10 years, you should have that amount in your account. Okay? So it's literally just plugging into the formula and then using your calculator. Now, example 2 is a little bit trickier, all right? This one is going to be not looking for C, we're going to be not looking for Y, we're going to be looking for C. Okay, well, I kind of gave it away, but let's go through this, okay? How much would you invest at 3.5% to withdraw $2,900 after 4 years, okay? So with these kind of problems, you have to be careful if you're looking for Y for the end result or C, the starting amount. So the question is, how much would you invest? Is that Y or C? Well, when you invest, that's what you start with. We're actually looking for C in this case, right? That's how much you would invest. That's how much you start with, right? Okay, what's our R? It's how much would you invest at 3.5% to withdraw $2,900 after 4 years. Our R is, now we got to be careful, 3.5 is it's a decimal, but it's not the right decimal. We got to move a 2 to the left still. It's going to be 0.035. To withdraw $2,900 after 4 years, that's going to be our Y is $2,900, what we ended with, and our time is going to be 4. Okay, so let's plug it in now. So we have Y, we're going to plug into this formula, Y equals C, 1 plus R, all to the T. So we're looking for, we know what Y is, that's 2,900, equals C times 1 plus 0.035, all to the 4, to the 4th power. Now, 2 ways you can approach this. The way that I would do this, the most accurate way to do this, is to divide both sides by 1 plus 0.035 all to the 4th power. So you could do this, divide by 1 plus 0.035 all to the 4th. This is the most accurate way to do it. Or you can just put 1.035, that'd be fine too, okay? That's going to give you the most accurate answer, which C is going to be approximately, if you do that, that's going to be $2,527.18. Okay, the other way you can do it, if this is too complex for you, which is totally fine, I'm going to get my calculator here so I can do it here. The other thing you could do is you could calculate, so go back to that last step here. Actually go a little bit lower. We're going to go back to this step. So another thing you could do is you could calculate this and then just put that in front of C. Let's go ahead and do that. So I'm going to do 1.035 to the power of 4. So it's approximately 1.15. So I'm going to put 1.15C, and then I can divide both sides by 1.15. So you can do an approximation and then divide by that number too. That's a little bit easier. That's easier, but it's not the most accurate, but I'll still accept it if you do it this way. And if you do that, we're going to do 2,900 divided by 1.15. If it wants to work. So I got approximately 21.74. You see how the numbers are a little bit different, right? This one was 25.27, so it's a few dollars off. But if that's makes more sense to you to do it that way, feel free to do it, okay? But otherwise, just divide. This is just a number here. This is just a number. So we can divide it by that number. Even though it's a weird thing, we can still divide numbers by numbers, right? We can divide C both sides by numbers, all right? All right, let's talk about a couple more here. 50 chipmunks are released into Hickston Forest. Chipmunks triple in population each year. Okay. What is the percent increase each year? All right. So when it says triple or quadruple or anything like that, that's going to be our growth factor, okay? That's our growth factor, which is 1 plus R. So if triple means what number usually? Triple means 3, right? So I'm going to do 1 plus R equals 3. Now, how do I solve for R here? What am I going to do? I'm going to subtract 1 from both sides. I get R equals 2. All right, R equals 2. Now, remember, this is a decimal. We need to convert it to a percent now. We're looking for a percent of increase, okay? So I'm going to move the decimal 2 to the right now to go the opposite direction. And R is going to equal 200%. It's a 200% increase every year. Okay, so be careful. If you're given R, you need to move it to the right too. And if you're looking for R, you move it to the left. And what will the population be after 4 years? Okay, so what's our C? What's our starting amount of chipmunks? C was 50, and they triple each year. So we're going to do Y equals, remember, it's C times 1 plus R all to the T. So Y equals 50 times 1 plus R, we said was 3. Or triple, you could do 1 plus 2 if you wanted to, all to the 4th power. When you do that, you're going to get 4,050 chipmunks. Okay? So that's a really big increase. 200% increase every year gets to, after 4 years, you're going to have 4,050 chipmunks. Okay, last example for today. You invest $100 on your birthday in an account at an annual compounded rate of 4%. What will the balance be over the next 20 years? All right, so again, we're going to do Y equals C times 1 plus R all to the T. Okay, what's our starting value? Our C is $100 we started with. What's our rate? It's 4%. What's that as a decimal, though? 1, 2, it's 0.04. Good. We're looking for the next 20 years, but all this table is wanting you to fill it in every 2 years, basically. So our answer is going to be, or our equation is going to be Y equals 100 times 1 plus 0.04 all to the T. Okay, and then you would plug in for T these numbers. You'd plug in 2, and then 4, and then 6, okay? So make sure you try that for a couple of them to make sure you get the idea down, but here's the answers you should have gotten. You should have gotten 108. You can pause the video if you want to try to fill these out yourself. Give them a try. So we had 108, we had 117, 127, 137, 10 was 148, 12 was 160, 14 was 173, 16 was 187, 18 was 203, and 20 was 219. Okay, we're not actually going to graph it because I don't think the graph is going to be super useful, but what I want you to fill in the box here is exponential is not a straight line, so it's not linear. Okay, it's not a straight line, it's not linear. I'm going to draw a couple of graphs here that are going to be a good representation of what exponential growth and decay looks like. So here's growth. Okay, growth is going to look like this. It's going to go very steep, very fast. It's going to be curving upwards at a very quick rate. Okay, it's going to go like this. It's not perfect, but that's exponential growth. Decay, let's use red, it's going to be going the opposite direction. It's going to be curving down. And it's got kind of sloppy there at the end, but it'll go down. Let me fix that. You won't be able to see that. It's hard to do this like this. Let's try like this. It actually won't always reach 0. It might actually go a lot farther down this way. Might actually go a lot further down this way before it gets to 0. So, but this is going to be decay. We'll talk more about decay in 8.6, okay? But exponential growth gets very, very quick, very fast, and it's not a straight line. Do you see how it's not a straight line like well, you're not going to see that. It's not a straight line like this blue line here. Okay? It's not a straight line. It's going to be a curved line curving up very fast or curving down very fast for decay. All right, that's all I have for you today. Thank you for watching. Have a great day. We will talk soon.